All right, we got a second day of 8-1. Students will be able to find the explicit rule for geometric sequence. And this is page 4 and 5 of the packet. Then I ended up printing it out anyway, so I'll try not to do that from now on. Hate wasting paper. But anyway, give the following arithmetic sequence. Oh no, I'm up here. Find the first 4 terms and the 8th term for the recursively defined sequence. Recursive means the nth term of our sequence is defined using previous terms. So the one we're on is, in this case, the addition of the previous 2 values. So the third one is -1, and then -1 plus 2, because it goes -3, 2, add those 2, add these 2, add those 2, add those 2. What do they want, the 4th term? 1, 2, 3, 4. So I got that, and then the 8th. 1, 2, 3, 4, 5, 6, 7, 8. Here's the 8th term. Do you recognize this or not, or is it not enough? What's that starting to be? Fibonacci, right? Because then it'd go 3, 5, 8, and so on. Given the following arithmetic sequence, -2, 1, 4, 7, the common difference is 3. We're adding 3 every time. The 8th term, so 5, 6, 7, 8. Recursive rule for the nth term. A sub n equals a sub n minus 1 plus 3, but a sub 1 is -2. I kind of did that out of order, but it's not a big deal. An explicit rule for the nth term. Explicit rule. This is arithmetic. So a sub n equals the slope, or the common difference, is 3. But if I plug 1 in for n, that's 3. I don't want it to be 3. I want it to be -2. So we'll just minus 5. And now we start the first one out at -2. This is all review, so we're going to zip through this pretty quickly. When we hit the calculus part of this, then we'll slow down. Common ratio for this one is -3. We're multiplying by -3 to get those. The 9th term, holy cow. If I go 81 times -3, that's the 5th. 6th, 7th, 8th, 9th. So a sub 9 is equal to -19,683. So in other words, we just keep multiplying by -3 till we get to the one we want. A recursive rule. A sub 1 equals -3. A sub n equals a sub n minus 1 times -3. An explicit rule is a sub n equals a sub 1 r to the n minus 1. So that's -3 times -3 to the n minus 1. However, if we have -3 to the first times -3 to something else, we can add those two. And when you add 1 plus -1, you could write this as -3 to the n. But that's only if the bases are the same. If a sub 1 is the same as the base as r, then you can combine those. But that's even not that big of a deal. We've done this technique right here for this problem in exponential decay. So it says the 2nd and the 7th terms of a geometric sequence are, this is the 2nd term, this is the 7th term. They're -1/2 and 16 respectively. Find the following, the common ratio. Well, I know that -1/2, whoops, not 12, -1/2. -1/2 is equal to a sub 1 r to the 2 minus 1. It's the 2nd term. And 16 is equal to a sub 1 r to the 7 minus 1. It's the 7th term. I think I'm going to write it like this. I think I'm going to write this one first. 16 is equal to a sub 1 r to the 6th. And -1/2 equals a sub 1 r to the 1st. Well, now, because this is multiplication, a sub 1 times r, a sub 1 times r, I think I'll divide these two. 16 divided by -1/2 is -32. And here's why I'm going to divide it, because those cancel out. And we have r to the 5th. Because when you divide, you subtract the powers. So if we take the 5th root, r is -2. So there's the common ratio. They want the first term. Well, if I plug this into somewhere, I don't know. How about plugging it into this one right here? Negative 1/2 equals a sub 1 times 1/2 to the, oh, it's just 1/2 to the first, right? 2, not a half, 2. Is that what you're going to say? Yeah, not a half, 2. Negative 2 to the first. When I divide by negative 2, a sub 1 is 1/4. So the explicit rule is a sub n equals 1/4 times negative 2 to the n minus 1. I had 1/2 on my mind the whole time. So you'll have to use that in the homework today. Division is kind of the key there. Divide them out. Do a system of equations, divide it out, and you got it. And then this is just an example of the homework instructions. Let's go through this very quickly. Common difference, we add 5, looks like. The 8th term, let's see, the 5th term, 6, 7, 8, what one? 9th term? 8th term, I got it. 1, 2, 3, 4, 5, 6, 7, 8. I went one too many. C recursive rule, a sub 1 is negative 6, and then a sub n equals a sub n minus 1 plus 5. So there's the recursive rule, and then the explicit rule, a sub n equals, the slope is 5, but I need negative 6 when I plug 1 in. So I need 5 times 1, plus something to equal negative 6. So it's really negative 11. Because I need to get that first term. We don't do arithmetic very much in this chapter. It's pretty much all geometric. Just arithmetic aren't that interesting. Geometric, much more interesting. All right, speaking of geometric, A, the common ratio, is 1/3. That's right here. We're multiplying each one by 1/3. The 9th term, let's see, I got 1, 2, 3, I got 4. So if I just take 9 times 3, that's the 5th, 6th, 7th, 8th, 9th. So 2 over 2,187 is the 9th term. Is that what they wanted? Yeah, the 9th. C, a sub 1 is equal to 6. And then a sub n equals a sub n minus 1 times 1/3. There's recursive. And then the explicit, a sub n is 6 times 1/3 to the n minus 1. And it's n minus 1 because we don't want to multiply by 1/3 until the second term, not the first term. First term, I don't want to multiply by anything except 1. All right, that's a review of, we did that in pre-calc. You might even covered it in Algebra 2. So a lot of review there. All right, the new stuff. Because the homework is so kind of just all review, I thought, well, let's have a sneak peek of what we're going to do tomorrow. This is way more interesting. This is kind of instructions to me. Approximate f of x equals sine of x. Approximate this function centered at 0 using linear approximation. Then we'll extend that to higher order polynomials. Write a 7th degree Taylor polynomial, compare it to sine x in a calculator, and forget about the rest of it. All right, so a linear approximation. We've done this, where we have the point, and we have a slope, and then we write the equation of a line to approximate a curve at a point. So we need the derivative. F prime of x is equal to, we're taking the derivative of sine, which is cosine of x. So f prime of 0 is cosine of 0. 1. Well, we have y minus 0 is equal to 1 times x minus 0. There's the line that approximates the curve. In other words, it's y equals x. Here's sine, roughly. And we're using a line, y equals x, to approximate the curve at 0. All right? So here's 0, 0. Can you see the line is a good approximation for a while, but then it gets really bad. If I want to approximate this point using that point, those are two pretty close together. So if I take the sine of 0.1, which is close to 0, there's the answer. And if I plug 0.1 in for x, I get 0.1. Well, that's 0.1. Isn't that roughly 0.1? Pretty close to 0.1, right? Pretty good approximation. But over here is pi. So what if I took the sine of pi, but backed up a little bit? There, I backed up just a little bit from it. Oh, I have that. Sine of pi minus back up a little bit. All right, there's the sine. But if I plug this in for x, that's supposed to be an approximation. This is supposed to be an approximation of this. But if I take pi minus 0.1, that's really, really bad, because I'm right here on the curve, and I'm saying this is the approximation. Really bad, isn't it? Because we're way too far away from the point of tangency. It got really bad, because sine is definitely not linear. Okay, can we do better? Can we use a quadratic equation to approximate this? It doesn't have to be a line. Can I use a parabola to approximate it? Let's find out. I need a function where I plug in 0, 0. The first derivative is 1. And let's see what the second derivative should be. All right, so here's the second derivative. Negative sine of x. So the second derivative at 0 is negative sine of 0. It's 0. Oh, okay, so let's try that. Let's try to write it anyway, even though the second derivative is 0. F of x would be, let's take this, x, and we're going to add on 0x squared. Now, I need everything to fit. I need the point to be 0, 0. I need the first derivative to be 1, and I need the second derivative to be 0. Well, if I plug 0 in here, I get 0, 0. First derivative would be 1 plus 0x, let's say. So if I plug 0 in there, the first derivative is 0, and the second derivative is 0. So first derivative is 1, I think I said 0. First derivative is 1, second derivative is 0. Everything works. This function works, but it's not a quadratic because this ended up being 0. So let's skip that. Let's go to cubic right here. I need a function whose point is 0, 0, whose first derivative is 1, second derivative is 0, and third derivative negative cosine. Now, if we plug 0 in there, that's where we're centering this. We're centering when x is 0. We have negative cosine of 0, negative 1. Oh, okay. All right. Now I'm going to write f of x as x minus x to the third. I'm going to skip this part. It ended up being 0. Throw that out. Forget it. So I don't have a quadratic, but I have a cubic. If I plug 0 in, do I get 0? Is that good? Okay. Let's see what the first derivative, we're not going to do this every time. First derivative is 1 minus 3x squared. If I plug 0 in, I get a slope of 1. I needed that. Second derivative is negative 6x. If I plug 0 into there, I get 0. Good. Third derivative equals negative 6. Oh, no. I need it to be negative 1. Dang it. I got the 0, 0. I got the first derivative. I had the second derivative. And the third derivative is messed up. However, let's look at this. If I divide by 6, does that mess? That would get the third derivative, but that would get the third derivative. I'd get the negative one I wanted, but it doesn't mess anything else up before that. If I plug 0 in here, I get 0, don't I? Didn't mess that up. If I take the first derivative and plug 0 in, that's 1. So I still get the first derivative. Second derivative, if I plug 0 in, I still get 0. Third derivative now is exactly what I wanted. I like this. I like this. It gets everything I need. Fourth derivative is going to be 0 again, because the fourth derivative, I'm running out of room, is sine of x. 0. So I'm not going to worry about tacking that onto this. Let's go one more. The fifth derivative is cosine of x. We've kind of started back to where we are. It's periodic. Sine's periodic, so now we're back to here. But the fifth derivative is 1. All right, I'm kind of all over the place here. I'm going to add on to this function right here. I'm going to say that the fifth derivative fits like this. X minus x to the third over 6 plus x to the fifth. But remember, I need the fifth derivative to be 1. And we're going to have a problem. But look, there's kind of a pattern going on here. If I take the fifth derivative, I would get 5x to the fourth. There's the first, second, third, fourth, fifth. But isn't that 5 times 4 times 3 times 2 times 1? Do you see that as you take the derivative? What is that? Factorial, isn't it? So I got to divide. I'm going to erase this. If you left room, you don't have to. I need to divide by 5 factorial. And here I'm going to let you in on a little secret. We're dividing by 6, yes, but we're really dividing by 3 factorial. Now this says, write a 7th degree Taylor polynomial. We've written the 5th degree Taylor polynomial to approximate sine. The 6th derivative would be 0. The 7th, do you see how it goes plus, minus, plus? It probably is minus x to the 7th over 7 factorial. That's the pattern that we would have. Okay, so what? What'd we do? We have a polynomial, and we write it like this. P sub 7, the 7th degree polynomial, because it's not f of x. F of x is sine of x. It has to be something else. And we say it's P of 7, P sub 7. If I take, let's find this. Let's find P sub 7 of 0.1, and we'll compare that to f of 0.1. So sine of 0.1. That. 0.099833466. Now let's go 0.1 minus 0.1 to the third divided by 6 plus 0.1 to the fifth divided by 120 minus 0.1 to the 7th, and I don't know what 7 factorial is, divided by 7 factorial. All right, here we go. How many decimal places do you think this is going to be accurate to? Any idea? 6 decimal places? There's 10 up here, by the way. So you're going to say it's good to 6 decimal places. Okay, that's a pretty good guess. A pretty good guess. But it's all 10. Isn't that amazing? We only went to the 7th degree. We only have 4 terms, and we're already accurate to at least 10 decimal places. At least 10. Could be more. So we don't even know what the error is. Our calculator doesn't even go out far enough to even decide what the error is on this, because it is an approximation. No matter how many you go, it's only an approximation. It will fail somewhere. But it could be 30 decimal places down the line where it fails. Well, so what, right? You're like, who cares? Well, without this process, these don't These aren't possible. Your calculator does not know what the sine of 0.1 is. It doesn't know. It has no clue. What it does do, and I don't know how it does this, don't ask me that, it turns sine into this polynomial, and your calculator only knows how to do polynomials. That's it. It only does polynomials. But it knows how to turn everything into a polynomial. It knows how to turn natural log into one. It knows how to turn e into one. It knows how to turn square root into a polynomial. Anything that's not a polynomial, it knows how to turn it into it. How does it do that? I have no idea. I've Googled it. I can't figure it out. But it does. Now this is kind of cool. Prepare to be amazed. Yeah, shut it. There's the line. Here's the cubic. Here's the quartic. Here's the, no, that's the quintic, I think they call it. Here's to the 7th. But notice that it's getting more accurate down the middle, but it's getting more accurate wider as well. So yeah, it's like perfect down the middle. If you go just slightly off of 0, you're going to be accurate to 7, 10, 12, 15 decimal places. But it's getting better wider as well. So the more terms we add, and I would argue that going to x to the 9th is not really that far, but look how accurate it is. Look how it's following sine perfectly for quite a while. So you can center at 0 and be pretty far away, still have a very accurate answer. Now, if you're centering at 0 and you start plugging in 6 radians, you can see how it fails very quickly once you're out of what we call the interval of convergence. So there's an interval of convergence. Once you start getting out of there, it fails pretty hard, especially with shooting straight up. That's what an x to the 9th does. It eventually shoots straight up. Imagine using that to estimate over here at 10 radians. Forget it. You're going to have to add on a lot more terms. But I think that's pretty cool. The interval of convergence for sine is infinity. It will converge infinitely as long as you keep adding on more terms. Let's try something that's not sine. Oh, by the way, before I did forget, is sine an odd or an even function? Odd, right? Because if you have the symmetry is through the origin. It's an odd function. It's symmetric over the origin. Well, look what the powers are. They're odd. They have to be. It's an odd function. It can't be even. You can't have an even function, even power on an odd function. It's not odd anymore. You will have to eventually memorize this. Not quite yet. We're ahead of the game. Here's another one you'll eventually have to memorize. Approximate f of x equals e to the x centered at 0 using linear approximation when we will, then we'll extend to higher order powers, write a 7th degree Taylor polynomial for e to the x, use to approximate f of 0.1. What is the error in the approximation? What is the error for 0.9? Forget, we're not going to do that piece. All right, so our first step, f of x is e to the x. Our first step was plugging 0 in because we're centering at 0. E to the 0 equals 1. F prime of 0 is also e to the x, but when we plug 0 in, we get 1. And all of these will be 1. The 7th derivative is 1. All of them are 1. Because the derivative e to the x is e to the x. So the polynomial is pretty straightforward. It's, if we're going to do the 7th degree, we're going to do 1 plus x. You know, if you plug 0 in, you get 1. If you take the derivative, you get 1. Plus x squared over, we better do it over 2 factorial, so when we do the second derivative, it eliminates, it gets rid of the fact that we did 2 times 1 when we took the derivative. X to the 3rd over 3 factorial, and we'll keep going. that polynomial estimates e to the x. That's what we're trying to find. A polynomial that your calculator will be able to use to evaluate e to the x. So let's see how good it is. The other one was 10 decimals good. Let's go with 0.1 again. This is definitely tedious. Where's my calculator? Here we go. 1 plus 0.1 plus 0.1 squared divided by 2. Mess that up. There we go. Yeah, let's do this. Plus 0.1 to the third divided by 6 plus 0.1 to the fourth divided by 24 plus 0.1 to the fifth divided by 120 plus 0.1 to the sixth divided by 720. Except for that little mistake there. Because I've memorized the factorials, I can put that in pretty quick. I mean, sitting there watching me has to be thrilling. You got to admit that didn't take me very long because I knew the factorials. The better you know them, the quicker you're going to be at this. Plus 0.1 to the seventh divided by 7. I don't know that one. I probably could memorize it, but I haven't. All right, here we go. Let's see how good it is. And that is supposedly approximates e to the 0.1. Not bad. Not a bad approximation. So 1.105170918. But f of 0.1 is exactly the same. Our calculators aren't even good enough to show that there's any error in that. So what is the error? Error in, how about p of 2 of 0.1? Let's do something we can actually look at. Can I start deleting these? Probably quicker just to type it in. 1 plus 0.1 plus 0.1 squared. Yeah, much faster, divided by 2. So there's the approximation. And if I go minus, this might end up being negative, but I don't care about that. There's the error. So the error in that is 0.000170918. Now remember, it's only an approximation. No matter how many terms you have, you can have 1 billion terms, it's only an approximation. It'll fail somewhere to the actual value. Now what happens when the derivatives are not 1? I want to add this one. All you got to do is write down this right here. You should have plenty of white space down at the bottom. We looked at sine, which derivatives are 0, 1, and negative 1. And then we looked at e to the x, and all those derivatives are 1. Well, what if they're not always 1? So f of 0 is e to the 0. Well, let's do it like this. E to the 2x, which is e to the 0, which is 1. F prime of 0, I'm doing 4th degree, is 2e to the 2x. When you plug 0 in there, you get 2. Second derivative is 4e to the 2x, which is 4. Third is 8e to the 2x, which is 8 when you plug 0 in there. And finally, the fourth derivative, we're doing 4th degree Taylor polynomial, is 16e to the 2x. And when you plug 0 in there, you get 16. So now the derivatives aren't just 1s. So the polynomial of 4th degree of x is equal to 1 plus 2x plus 4x squared over 2 factorial plus 8x to the third over 3 factorial plus 16x to the fourth over 4 factorial. Now the ones that we don't write, this is over 1 factorial, and this is over 0 factorial. But I usually don't write those because both of those are the number 1. We're dividing each by 1, so I don't usually write those. But they're there. Now if you really want to get ahead of the game, we can write this in sigma notation. This will be part of where we're headed. This isn't for a while yet. If I wanted, I think I would like to start this when it's 0. You can start sigma anywhere you want. You could say n equals 27 if you want. You could say n equals 389 if you want. But I wouldn't make it that complicated. Usually we start these at 0 or 1. And because this is really x to the 0 over 0 factorial, I'm going to start at 0. Now we're going to 4. So this is 2 to the n, because you have 2 to the 0, 2 to the 1, 2 squared, 2 to the third, 2 to the fourth. So 2 to the n. X to the n, 0, 1, 2, 3, 4. And that's what we're plugging in. N equals 0 to 4 means plug in 0, 1, 2, 3, 4 over n factorial. Then later on, we're going to do what's called the ratio test and decide what the interval is that makes this converge. For what values of x does this converge? And we do a whole bunch of other things with it. They're kind of fun. There's a sneak peek into pretty much the rest of the chapter. Yeah, I think that's all I got. Pretty cool stuff, actually. No applause necessary.